cosmic microwave background, or CMB, is the fossil remnant of the fireball of the Big Bang. In my last two videos, I told you what we know about it and the lessons it has taught us. In this video, I want to tell you about some things that we don't understand, which may or may not teach us something totally unexpected about the universe. It's going to be fun. In the last two videos, I told you how the CMB came to be and then what information can be extracted from the tiny temperature variations in the CMB that were discovered in 1992. They were caused by sound waves that existed in the cosmos when the universe was 0.003% of its current age. Personalizing it, for me, that's equivalent to when I was a mere 12 hours old. But let's take another look at the speckle pattern and see if we can spot anything weird. However, before we do that, let's take a little dive into some simple math. Let's start by looking at this mathematical function you see here. It's definitely a bit on the weird side with all sorts of upward and downward wiggles. Now, when physicists, mathematicians, and electrical engineers see that sort of thing, they immediately ask if the function can be broken down into a mix of sine and cosine waves. You can see a few examples here. This form of mathematics is called Fourier series analysis, and when you apply the proper techniques to it, what you find is that the wiggly function is a mix of pure sine waves. Breaking it down, you find that it is 10% the least wiggly sine wave, plus 20% the second most, 30% the third most, 10% the fourth most, and finally 30% the fifth most. This mathematical approach is similar to the one used to figure out what messages the CMB is telling us. I've shown you this picture of the CMB before. It was taken by the Planck satellite and the final version was released in 2018. The red spots are slightly hotter than average and the blue spots are slightly cooler. And I do mean slightly. The variations are less than 0.01%. If that image is a bit confusing, think of the CMB as like the surface of a golf ball. The golf ball is basically a sphere, but it has small dimples that make it ever so slightly bumpy. So how do cosmologists characterize the CMB? Well, just like that wiggly function example I showed you, they do a similar thing but with the spherical functions. These spherical functions are analogous to the sine waves we just saw, although the actual functions are called spherical harmonics and involve some complicated functions called Legendre polynomials. But don't worry, you don't need to know any deep math. We'll just do it with pictures. Rather than looking at a full 3D sphere, let's start by looking at the sphere side on, which gives you this circle here. The simplest equation with any wiggles at all has a difference between the north and the south pole, with one side hotter and the other side colder. That's basically equivalent to the one wiggle case. The next most complicated pattern is still hot on one pole and cold on the other, but it has additional hot and cold stripes. That's equivalent to the two wiggle case. The spherical situation is more complicated than the one-dimensional function case because there can be wiggles both going from pole to pole and also going around the equator. For instance, here is the spherical function with 2 wiggles going around the equator and 7 wiggles going from pole to pole. Scientists take many different spherical functions with all sorts of wiggle patterns starting from the simplest dipole with a wiggle up and down. That's 2 wiggles, hence the prefix di. Then there is the quadrupole with a total of 4 ups and downs. After that, there are octupoles with 8 and so on, all the way up to the 4,000 pole, which doesn't have a snazzy name. Add a smidge of one wiggle pattern and a dash of each of the others, and you get the CMB. So that's how it's done. That's not a mystery. The mystery arises when we take a look at the orientation of all these spherical functions. Each one of them has an axis. The axis is usually not too hard to determine. Imagine an American football, which is kind of a distorted sphere, longer in one direction than the others. The axis is along the long direction of the ball. And all of the other spherical functions also have axes too. Now we're getting to where the mystery arises. by all rights, the axes of all these functions should be oriented randomly, pointing in any old direction. There should be no preferred direction. However, when we look at the axis for both the quadrupole and octopole, they seem to be more or less in the same direction. Even weirder, they seem to be aligned with the axis of the solar system, which is perpendicular to the plane in which the planets orbit. On top of that, the dipole is oriented about 90 degrees from the other two, more or less in the same plane as the solar system. And the solar system seems to be moving basically sideways through the rest of the cosmos, like an oversized frisbee. Now, this makes absolutely no sense at all. The CMB shouldn't know about the Earth. The CMB was created about 14 billion years ago, and the solar system was only created about 4.5 billion years ago. It beggars the imagination that there should be any linkage between the solar system and the CMB. For this reason, astronomers have called this alignment the axis of evil, which does make me wonder, who could have discovered it? Could it have been Dr. Evil? No, it wasn't, but it should have been. Am I right? So this odd alignment could be simply by chance, or it could be that the data analysis techniques have subtly shaped the data. It's really unlikely that the alignment has any cosmic significance because it would negate a lot of what we think we know about cosmology. So some cosmologists are still poking at the data, trying to figure out what the axis of evil means, or if it's just a statistical fluke or an analysis artifact. But the jury is still out on the whole thing. If the axis of evil isn't tantalizing enough, there's another fascinating feature in the CMB that hasn't yet been satisfactorily explained, and it's the cosmic cold spot. When you look at the CMB as recorded by Planck or its predecessors, you see speckles and splotches. The red spots are hotter and the blue spots are colder. Now, the variation isn't much. Remember that the temperature of deep space is about 450 degrees Fahrenheit below zero for my American viewers, negative 270 centigrade for most everyone else, and 2.7 Kelvin for the scientists. And it's very uniform. Those red and blue spots only differ by about 18 microkelvin up and down. They are really very small variations. However, there is one spot that is very puzzling, and it's called the cosmic cold spot. While an 18 microkelvin fluctuation is pretty normal, the cold spot is, on average, 70 microkelvin colder than normal. And in the coldest spots, the temperature is a full 140 microkelvin colder. If you run the numbers, you see that this is a statistically unlikely anomaly. Using the rest of the sky to guide the prediction, the probability of seeing such a spot purely by chance is about 2%. And the spot is big. It's about 5 degrees wide, or about 10 times wider than the full moon. It's located in the southern hemisphere and the constellation Eridanus. The apparent coldness of the spot is exacerbated by the fact that it is surrounded by a hotter ring. So what could cause the cold spot? Well, the easiest explanation is that the universe just happened to be created that way. That's a possibility. However, other explanations have been suggested. Perhaps the most speculative idea is that the cold spot is a bruise left on our universe from a collision with another universe immediately after the Big Bang. That hypothesis is really implausible, but it has been suggested. The most likely explanation is that there is a huge supervoid between the CMB and us. A supervoid is a region with essentially no galaxies, an empty hole in space. The idea is that light from the CMB enters the void. Because there is no matter there, the light loses energy as it pulls away from the matter-dense regions. Now, everything being equal, it would gain energy as it exits the void, and the photons of light would emerge with the same energy as they entered. This is like someone on a bike trying to coast over a small hill. They slow down going up the hill, but speed up on the other side. If friction wasn't a factor, the whole thing is a wash as far as energy is concerned. However, as the light crosses the void, the universe is expanding and stretching the wavelength of light. Longer wavelength means lower energy, and that means the photons of light leave the void with lower energy than they entered it. That would make a cold spot in the CMB as we see it. Now, people have looked for a void in the direction of the cosmic cold spot. While there is some controversy about this, some have suggested that the void would be nearly 2 billion light-years across, and it would be located at least 3 billion light-years away. Other studies have suggested different distances and sizes of the supervoid, while other studies question the existence of the supervoid at all. The bottom line is that the question is still under debate. So what's the answer? I don't know. I think a supervoid is substantially more likely than colliding universes, but we're going to have to wait and let the data do the talking. You know, the CMB is really a pretty cool thing. It proved the Big Bang, and it showed us the minimum size of the universe. It showed us how fast the Milky Way is moving compared to the rest of the universe. And it has left us a few mysteries to solve. Were I a betting man, I'd bet that the CMB still has something to teach us. Further study will reveal surprises that we haven't anticipated. And I haven't even mentioned the possibility that the CMB will prove or disprove the idea of cosmic inflation, the idea that the universe expanded faster than the speed of light shortly after it was born. I think the bottom line is that the CMB will continue to fascinate scientists for decades. Okay, that was pretty cool. If you enjoyed the video, I hope you'll like, subscribe, and share. The idea that we can learn so much from such a subtle measurement isn't so unusual. We see it all the time when we use our physics knowledge as we explore our data, proving once again the thing that we all know, which is that physics is everything.